Wow, it's very impressive. How often do you get a greeting from the president of Portugal? Every day? No? It's a hard act to follow for me here. So I'm under a lot of pressure to give this talk here. So I'm glad to be here. I'm based in the Silicon Valley, and it's got a chance to see a lot of the exciting AI going on in the Valley. Earlier this year, sometime in February, I wrote a blog with this title, Unlocking Generative AI with Ubiquitous Hardware and Open Software. And I posted on LinkedIn and got a very strong positive feedback for this. And I was a little bit surprised by this. I thought I'm just going to write one of these blogs here. So appear to be there's a lot of interest in the community for this topic. So what I want to do here is I want to share the same with you here today. Now, obviously, a lot has changed in this AI era. Things happen very quickly. So we update a lot of content here, but the idea remains, which is great. So it's not surprising we have a huge opportunity in front of all of us here, which means we have a chance to get to AI everywhere. And from where we stand, we got a chance to see many AI applications across multiple industries. So that's a good thing about working in a big company. We got a chance to work with many customers. And some of these you're probably familiar with. Probably the most mature industry using AI is the cloud service providers. And they have a lot of data, and quite often they use recommendation systems underneath to do these. And we worked with healthcare, as the president mentioned earlier. Healthcare remains sort of the number one interest for a lot of people. It's one of these personal passions for me as well, just to see whether we can apply AI in healthcare. And quite often underneath healthcare, you have a variety of AI techniques used there as well. For example, you can use computer vision for radiology, and you can use natural language processing to process a lot of doctors' notes, which are not easy to understand. And we can use, for example, graph computing to do drug design. So we've been working with some drug discovery companies to do drug design using graph analytics and GNN, for example. Now, most recently, we've been looking at generative AI. And as an industry, it is such a huge change in the last about a year, even less than a year, in terms of generative AI. So naturally, we're getting into generative AI as well. So for today's talk, I want to focus on generative AI. Obviously, we have done a lot across the board with all kinds of AI techniques, but generative AI seems to be the hottest topic today. So it has a huge potential. So I want to show you a little bit more about unlocking generative AI here. Now let me start with a simple example. So I'm sure you're all familiar with Stable Diffusion, right? You put in the prompt, it can generate some image for you. Now what's different here is we want to do it in such a way that it is efficient. So you don't need to have a large cluster of machines in order to generate images like this. So in this example, on the left-hand side, on the right-hand side, all you need to do is one of these CPUs you may already have, and that can generate image in a few seconds. So this shows with ubiquitous hardware, even a CPU can handle generative AI like this. And quite often you want to do fine-tuning. For example, you want to have your personal images and do fine-tuning so that the generative AI can give you the right images with your personal information inside. You can do this also with a machine like a CPU here. Now, this is just one example here. In order to get to AI everywhere, the key is actually developers. The key is actually people sitting here. And we have the data scientists here. I ran into a few of them in the minivan coming to the conference this morning. And we have the AI developers. Right? And once you want to go to AI everywhere, you want to reach a broad set of developers. And many of them are not necessarily AI researchers, and they are actually domain experts. They could be physicians, they could be somebody working in the industry for a long time, but they're not really AI experts. So the opportunity we have here is people have data and they want to get insights. Now, how do we make that happen in a seamless fashion? So there are two things I want to bring up here. One is obviously performance is important. So I'm coming from an industry where we develop infrastructure for AI. And performance certainly is important because AI is a very compute-intensive application. But that's not sufficient because when we go up to serve many developers, you want to make it easy for them to develop applications. So simplicity is equally important, if not more important, when you develop solutions. You want time to solution more than performance here. So let's look at the overall stack here. And in order to get to AI everywhere, in order to create generative AI at scale, we want to have open software and ubiquitous hardware because you want hardware to be available everywhere. You also want software where you can access openly. And particularly for generative AI, openness and transparency is going to be super important because all the things you hear about generative AI, there are things you just don't understand why they give you the answer that they did. So having an open software ecosystem is very much important. When we look at the entire ecosystem here, I see 3 different layers here. At the top, these are the models. And you will see more and more nowadays, there are all kinds of open source models available now. And there are a variety of these open source models, as small as 1 billion kind of size, all the way to very big. And then at the bottom, there's different types of hardware available nowadays for this. These are just examples of the different 3 types of hardware available here. And we happen to do all 3 of these 3 types here. So one type is CPU. Quite often, we actually be adding more AI acceleration inside CPU. And the second type is GPU. And the third type is special purpose accelerators. And within the industry, if you look at what everybody's doing, roughly they all fall into one of these 3 categories. Okay? And then in the middle, the software piece is going to be even probably more important. I'm maybe a little bit biased because I'm actually, for the most part, a software person, and we do work with hardware team closely. On the software side, we will have 2 parts here. One is it's critical for us to grow a healthy, open software ecosystem. And I'll give you one example of PyTorch. And I'll talk a little bit more over there in the next slide here. And the other is we want to make it easy for people to develop applications, as I mentioned earlier. So software is going to be key to provide a platform for data scientists or AI developers to develop applications. And one example I give here is from the Hugging Face side. Hugging Face is a level above. Hugging Face is a startup you probably know. They're building an ecosystem above the frameworks like PyTorch and TensorFlow. Now, these are just examples of what we have here. It's not an exhaustive list of every piece of software in the ecosystem here. Now, let's look at on the hardware side. So as I mentioned, the 3 different categories of hardware here, from CPU, GPU, and AI accelerators, purpose-built AI accelerator here. And most recently, Meta launched Llama 2. And Meta has been a great partner with us. We've been working with them very closely. So before they launched Llama 2, they asked us, they said, hey, can you guys work with us, be a partner to support the launch of open Llama 2 here? We say, yeah, of course, we want to do this. So as a result, we got a chance to access Llama 2 in advance, and we got a chance to measure Llama 2 on the hardware we have here. Now, I won't go into all the details here. This shows for a different range of large language models, you can actually have a variety of hardware available to solve these problems here. So from the customer perspective, usually what you want to do here is you want to have a good latency. For example, a latency within 100 milliseconds. And as long as you get to that level, you're fine, right? When you have a human interaction, you do need to have certain level of latency. Now, you can see from the charts here, for certain model size, CPU can do it. For certain model size, you need accelerator for this. For certain model size, you need a GPU for this. So there's a choice of the variety of hardware available to achieve the goal here, depending on the size of the variety of these models here. Now, that has implications of getting to AI everywhere, because you don't necessarily want to depend on a large cluster always to get the work done here. An example on the software side is we have been participating very closely with other companies on PyTorch. Actually, PyTorch, as you know, originally came out of Meta, and they donated to Linux Foundation. So now there's a PyTorch Foundation in the industry. So it is huge. It's a great step for Meta to make that move, because now it is owned by the community. And Intel happen to be one of the premier members on the foundation. So I'm actually sitting on the governing board of PyTorch Foundation, and get a chance to see how we can shape the future of PyTorch as a community here. And the other partnership we have here is Hugging Face. As I mentioned earlier, we want to move up the software stack to make it easy for people to develop applications. And Hugging Face has been doing a great job as a community for hosting a lot of machine learning models, and particularly for large language models. And they've been we started working with them more than 2-3 years ago, when they were still much smaller at that time, and focusing on, at that time, NLP was a pretty narrow niche of AI. Now you never know. 3 years later, they're big now. They raised a lot of funding recently. Their valuation is huge, for more than $4 billion valuation here, right? So this just shows AI can change very quickly. And the reason we've been working with them is we want to grow the overall ecosystems. That's just another example of making sure the ecosystem works well for everyone here. And the way we do this is we want to do optimizations of these models, and we want to upstream everything into the ecosystem. Same way we've been upstreaming to the PyTorch side, we've upstreamed to the Hugging Face side as well. And as a result, a lot of these models, more than 100,000 models on Hugging Face, have been optimized because of the efforts we made here. Now, in addition to upstreaming our optimizations into the ecosystem, we're actually creating new extensions. So this is an example of the extension we have created for the Hugging Face transformer. I'm sure you're all following transformers around here, right? Transformer is the hardest thing in the industry now, pushing the envelope of generative AI. So this just shows the example of a toolkit we provide. It's all open source that we have created, so people can easily create, for example, chatbots from this. We have a prototype of chatbot included already. So this is our attempt to reach as many people as possible, so they don't have to start everything from scratch. You already have a baseline chatbot, and you can use your own data to fine tune and get the information from them. Get additional customized chatbots for your own enterprise or own university. Now let's look at the model side. we also have been looking at variety of models here. So one example of this here is we've been working with Argonne National Lab back in US. Actually, I went to Chicago a couple months ago to kickstart the effort on generative AI, and the goal there was to train a 1 trillion parameter model for science. Because Argonne, their mission is to enable the scientific community over there. So we're looking at one end, which is very, very large models here. Now, not everybody can afford a supercomputer, right? Argonne National Lab, we've been working with them. We're creating a huge machine. The machine is going to have 60,000 GPUs inside. But not, I can afford a 60,000 GPU cluster here. Not everybody can afford that level of infrastructure. So how do we do this more efficiently? How do we do this thing? I mean, we do need large machines. We do need to push the boundary of these huge models. But if you want to get to AI everywhere, we need to reach millions of developers who do not have access to supercomputers. So how do we make it sustainable? Even you have access to it, it's very expensive to train these models. So sustainability is one thing we actually been looking at, and the other is responsible AI. And I ran into somebody in the car today, and she's looking at AI for good, right? And there's a lot of concerns about whether AI will bring the only value to you, or whether AI will do damage to human beings here. So one of the research projects we have inside our research labs is really looking at the efficiency. How do we make these smaller models work effectively? So this is just another example here. So when you look at things like ChatGPT, the model is pretty big, right? GPT-3 is known. GPT-3 is 175 billion parameters. And GPT-4, people are still guessing, right? Nobody announced it. People are guessing, could be hundreds, trillions, or could be some very large number, right? Now, this example shows if you use a technique called RAG, and with RAG, basically give you a knowledge base. So once you have a knowledge base as the front end for a large language model, with that combination, you can get great result without paying for the huge amount of resources for a very large language model here. So in this particular case, you can go from 175 billion to 7 billion in this case. So Akapa is actually a piece of research coming out of Stanford. At Stanford, and many of us in the community are pushing in the same direction here to get something smaller and more efficient. So let me just show you one example here. So this is a chatbot which takes a prompt which says, what is IDM 2.0? And that happened to be one of these Intel things. Okay, because Intel has been pushing for IDM 2.0. Now, if you only ask that question to a generic chatbot here, it will give you some answer at the top, which is the orange box, which has nothing to do with the Intel's IDM 2.0, because that generic chatbot was not trained for, in some sense, the personal data you happen to have. So with a RAG knowledge database with the special Intel information inside, the chatbot can give you the right answer here, which is about a Intel strategy called IDM 2.0. Now, in the same fashion, all of you, right? I don't know, whether you work for enterprise or you're in your university, all of you, even personally, you have your own personal data, either personal data or private data for your enterprises. And usually, the generic large language model does not have access to. And you probably don't want to give the data to a generic model either, right? And so this is an example where we can do better in terms of both for sustainability and also quality of your answers here. Now, sometimes you can also use fine-tuning tune the model directly. So the knowledge base is front end in front of a LLM. Here you can actually retrain the LLM. So this is more of retrain the LLM with your own data. So now you have a model itself can actually understand the private data you have, right? So in this example to show, once you have both, you can still use retrieval-based arrest and fine-tuning. And with both, you can get an answer which is both more accurate and also more succinct. The clarity of the answer you're getting over there. So these are the variety of techniques you can do to get a better answer more efficiently here. Now, the other interesting thing people started looking at, as I mentioned earlier, it's a question of AI safety. And that opens up a lot of challenges, also a lot of opportunities here. And as we know, when we interact with these generative AI models, and we have quite often get either the wrong answer, or the model basically makes things up, or you get an answer which is not good, right? It's biased answer because the data it got trained on is biased to begin with, and the variety of sort of issues related to generative AI here. And what we're trying to do here is on the software side to do two things here. One is, can we try to measure first, right? Because I'm always a believer where if you don't know how to measure it, then you cannot make progress, right? So first, can we measure these issues? Now, all of these is still a very much open research. So for some of you here, maybe you're ran into somebody who's a PhD student, right? We have students here. It's a good thesis topic for you, good PhD thesis topic for you here, right? And it's a very hard thing to do also. So one of the research projects I've run into is called HELM, HELM. It came out of a Stanford team, and it is I highly recommend that if you guys have a chance that you can go read that paper. The paper is a little bit long. It's more than 100 pages long. It's like a book, almost like a book here. And the other thing we've been doing is we're trying to create tools to help people when you develop models. You get awareness. You not only have the metrics, you also get the measurement. You understand whether something is good or bad, right? So this is another area where it is still emerging, and there's a lot of work to be done here. Now, the other thing we're doing here is because we are mostly, we're creating not only software but also creating hardware as well. So this is also our opportunity to add new features inside the hardware as well, and also leveraging the hardware features, for example, security, for making sure we have privacy preserving AI here. Now, this is the work from Stanford, the HELM project. And what they have done here is they have created many, many different scenarios. They have more than a dozen core scenarios and also more than 40 different kinds of scenarios here. So they start from a variety of scenarios for how to use large language model. And then they also create a pretty rich set of metrics to measure the different aspects of these models here. And for example, accuracy is obviously one thing you care about. And the other is like a fairness bias. So there are different ways of measuring whether a model is good or not. And they can track over time, for example, this is accuracy model, track over time how things progress in the last few years with different models people have come up with. And the accuracy obviously has come up in this case. Now, what I presented so far is what's going on today, right? For the most part, it's already in the market from both the hardware and the software side of it. Now, going forward, what will be the new idea that can dramatically change what we're doing today? And one thing we want to point out here is when we look at the AI today from both the software and hardware perspective, in order to get AI to give you the right answer, it costs us a lot, right? So we're talking about sustainability here, right? So we're talking about the supercomputer we're building in Argonne National Lab, 60,000 GPUs over there, right? And you all know how many GPUs, how many months it will take to train a large language model. It is very, very expensive. Now, this is another one of these research projects within our company here. They want to go back, look at the first principle here, which is look at nature, look at biology, look at all of us here. Actually, not more than all of us. Look at a bird. It's a cocktail bird here, which is a tiny bird, and look at how efficient. When you look at within the biology side, how efficient they can learn from there. The learning for a cocktail parrot, if you look at the brain over there, the power consumption is pretty low. It's 50 milliwatt here, right? And the bird, the in terms of weight, the mass is only 2 grams here. It's a tiny brain, but it can learn a lot. It can fly, and if you interact with the cocktail before, cocktail can also learn how to speak human language as well, right? So it is pretty smart with a tiny brain like this. Now, for a machine to do something similar, on the right-hand side, a drone, which is close to this, an autonomous drone, and if you look at the hardware, it consumes 18,000 milliwatt here. It is you can do the math here. I mean, a lot of smart people, you can do the divide here to see how many X this thing has here, right? And if you look at the mass, it's also pretty big, right? So we are still very far away from approaching how efficient we can do relative to biology here, to nature here. So the research here is to see whether we can change how you think about these things and make it more efficient. Now, if you look at the computing history, many of you have taken classes when you go to school. Initially, we start as a sequential machine, right? Sequential machine, you have a counter, you do one instruction at a time. And then in the last 20 years, it became more prevalent to do parallel computing. And then today, when you do deep learning, it's mostly parallel computing, parallel and distributed computing. You will need a huge number of machines to do this thing here. And the way we do this thing here is very much synchronous, right? When you think about how to do image recognition today, you take an image, you have all these pixels, and these pixels got converted into some number, a sequence of numbers somewhere, and turn out to be a matrix somewhere. And then machine learning basically is a lot of matrix computation, a lot of matrix multiplication, and you know the math over there, right? Now, that's a synchronous way of doing things, and because not every pixel is equal, actually, right? When you try to recognize an image, you only need to care about certain portion of the image. So the problem itself actually is pretty sparse. But the way we do things here is a dense way of doing things here, right? So the idea here is, can you go from a synchronous way of doing things to more of an asynchronous way of doing things, which is in your brain, you have many neurons here, and these neurons are operating in an asynchronous fashion. They are not really synchronized, right? So how do you emulate the real sort of brain to make it happen here? And this is one of these sort of still early days research we've been doing within the company. And we have developed some prototypes already in terms of both hardware side. The project is called Lohi. Right now is the second generation called Lohi 2. And we also built a system and a software stack on top of this. And we have demonstrated on the application side, you can do certain applications more efficiently. For example, you want to do airline scheduling or railway scheduling, you can do it more efficiently. But it's still early at this point. Now, to summarize, in order to unlock generative AI, we need both hardware and software. And we want to have ubiquitous hardware, and we also want to have an open software ecosystem so everybody can thrive in the environment. With that, we can get to AI everywhere. And on the AI model side, we all have seen a variety of AI models here, and it's still a lot of debate going on right now. There's one school which says, well, you want the largest models possible. You continue to push the frontier of the models. But there's also the other school, which is, can we make it more efficient? Can we have smaller models to do the same thing, and also in the privacy-preserving fashion? And then sustainability, environment is important to us. So AI sustainability and AI safety, they're both important to us. And if you have more information, you want more information, follow the link here. Otherwise, we are ready for questions. Thank you.
All right. Thank you very much for the nice talk. So before we kick off the question rounds, just wanted to remind you that you can ask your questions on the app. And as people are asking questions, you can also upvote if there's anything you really would like Wei to answer. So then we will go for the most voted questions. But I'll kick off maybe with one question that I have while they're still getting a hang of the app. So Intel, Intel started as a hardware company. You're basically doing hardware for, I don't know, when was Intel founded?
Oh, Intel was founded in 1968. It was many years ago.
Many years ago.
It was a startup many years ago.
Yeah, but now you already come to talk us about a bit software. So maybe you could do a little bit of how does hardware and software connect, especially in AI? How those things really intertwine between each other?
Yeah, so actually even a company like Intel, is going through the transformation. We have changed quite a bit. And we have many software people inside the company. And last time when we looked at it, we have more than 15,000 software engineers in the company. And if you pull the 15,000 people out, that can become a independent software company here, right? So I came in. I've been with Intel for more than 25 years now. I went in as a software person, as a compiler person for some of you who have done the compiler stuff. So and over time, I've seen the evolution of how software and hardware go together. Because as I mentioned earlier, many of these applications, particularly in AI, it became really a combined software hardware problem here. And luckily, we're able to do this well, in terms of getting both the hardware side and software side. Let me just mention two things here. One is in terms of co-design. When we look at how do you provide a solution, you want to look at it from both software and hardware perspective, right? And certain what kind of features you need inside hardware, you want the software team to tell you, because software teams are interfacing the developers directly. They understand what is the requirement on the software side, and so we can actually add the right features inside hardware. And then the other side is actually co-optimization. So once you have the features inside hardware, you need the software to help you get the best out of these features. So let me just take AI example. AI over time we have added a lot of matrix computation inside. We also added things like integer 8 data type support, right? Integer 8 is very important when you do inference, when you make inference run fast. Now, using integer 8 is not straightforward. You have to go through calibration and all these things. So actually create a tool called Intel Neural Compressor to help you make it easy for you to actually do the quantization. And quite often, it automatically do the quantization for you. So there's a sort of handshake and working together between hardware and software teams to make this thing happen here. It is truly a combination of hardware and software. So for those of you in the audience, if you're thinking about doing a PhD thesis or something, right, it could go either way actually. And quite often, it's very interesting to be at the interface between hardware and software, because quite often you need both.
Yeah. Right. And then as long as we're talking about integrating software and hardware, so there's a question with a lot of interest in the audience here as well, which is, to what extent does Intel use generative AI for chip design?
We are still exploring actually. So within Intel, we have something called long-range planning. We plan the new technologies as well, and one of these topics was actually how do you use generative AI for chip design. And so it is still early days. As I think most companies, when I talk to them, it's similar stage. Right? We've been using AI for a while now inside the companies. We've been using more of a, the AI changed so quickly. It's called traditional AI now, which was only happening a few years ago, right? So if you look at the evolution of AI, the early days of AI was more of a statistical machine learning, right? That's the XGBoost kind of AI, right? And then you get to deep learning. So now it's generative AI. So even a year ago, deep learning was a new thing. So now deep learning is also a little bit traditional. Right? So with the AI in general, we've been using AI inside the company to do development, to do validation, on a chip design here. And we actually even have AI inside the products we have shipped already. For example, if you have some of these laptops, if you have laptop, most likely you have one of these our laptops, and that actually has AI inside. Now, the AI used there is to do modulating the chip, so you can actually get more power efficient. Right? You want to have a longer battery life. So how do you predict when to turn things off and all that? So there's AI being used. Actually, AI is being used in a variety of things. We are a big company. Not only chip design, we also use AI for sales force, right? When you try to do custom engagement and all that. And one of the things actually we have done inside my team is building chatbots. So we have built 5 different chatbots. They're all POCs. It's not deployed yet. They're all POCs. So we're exploring to see how we can use generative AI for all the things we do here. It's still, I think it's still early at this point, but we're getting there.
Okay. So then there's a question: what is the AI firewall composed of? Where can we read more about it?
Yeah. So I'll find there's a paper published on the firewall already by another group, and we'll probably find a citation somewhere for you guys.
Okay. Thank you so much. And maybe just related to this, because there's also a lot of people asking if this slide deck will be shared, but maybe, or if you have maybe some kind of article or something that they can read further or refer to.
I think we can. I'll find a way to share the slide deck.
All right. Perfect.
we need to talk to legal and all that, but you should be okay.
All right. Then a question about neuromorphic. Mm-hmm. Do you think that neuromorphic could go beyond reducing the gap of the real brain, so let's say bird or human or any other animal, and where are we right now at this point in time in terms of efficiency? So like, where are we now, and how long do we still have left to go, in your opinion?
Yeah. So first of all, neuromorphic is not my expertise. It's So what I want to recommend is the head of the neuromorphic project called Mike Davis, and he actually has 2 videos online. Recommend you watch these 2 videos. It's all part of Intel All Access, Intel Architecture All Access. So you go to YouTube, you just look for neuromorphic computing Intel Mike Davis. You can find these 2 videos, and they'll be pretty interesting to watch these things. I think at this point it is still not quite ready in terms of replacing the birds yet, but it is a promising area. That's why we've been investing in this.
And I think we have time just for one more question, and this is, how does Intel make sure that AI safety and ethics are observed and not ignored? For example, when Microsoft fired its ethics society team in October 2022.
Yeah, so we are pretty big on the AI ethics side, and we actually have at the company wide we have a AI ethics council, and we have come up with a set of principles for AI ethics, and want to make sure we're doing things in a responsible fashion. Intel as a company is pretty responsible actually. We want to make sure, particularly when we develop new technologies, we develop in a responsible way. And in addition to these principles, as I mentioned earlier, we've been developing tools as well, developing software, and we also have been involved in many industry consortiums, and there will be new announcement very quickly, and we've been talking to a lot of people to make progress over there.